Hello, chemistry students. This week we get into what you will probably say, this is really chemistry now. All of the rest is foundational, but now we're going to get deep into atomic theory. And this is really where chemistry starts. There was a man named John Dalton, and he, in the early 1800s, was the first one who really gave us a developed atomic theory. Meaning, he said, let's look at these elements. And an element definition is really based on atoms, and atom definition is based on elements. But let's get there. He said, let's take a pure substance, something that is only one thing, not many things put together, or a mixture like we talked about last week. And he said, if you divide that substance up into its tiny pieces, he theorized that there was a tiniest piece that you could get to, and you could not divide it any smaller and still have it be the same substance. That's a pretty brilliant theory when you can't even see that small to even figure it out. And what his experiments had to do with was dividing substances up until he could say that they only divided up to a certain amount of mass or size, and you just couldn't get smaller than that. So he was measuring through experimentation tiny, tiny, tiny masses, basically saying that they only combined together in certain proportions, and so they had to be a smallest amount. Some quantum, I won't say that now, I shouldn't say quanta because that gets into even smaller, but some amount that things could get divided up into. And by the way, he theorized it was a sphere. So he was wrong about some things, but he really did some revolutionary experiments saying that it can only get down to a certain smallest thing. So we're going to say today that an element is a pure chemical substance that can't be divided into any simpler substance without it changing its character. So that's an element. You can divide it up only to a certain amount, but a substance has those certain characteristics that stay uniform in that element, even if you keep dividing it up to a certain point. And an atom is that smallest point to which you can divide it and have it still stay that substance. So knowing that, a whole lot of things that have been recorded for lots of years as pure substances, we could suddenly say, hey, we're going to give it a name, we're going to measure it, we're going to give it an atomic weight, which the first one to do that was Dalton, and we're going to start to tell you what some of its characteristics are. So now we know a lot more than Dalton did now, and that is even changing all the time. Like we have our atomic theory, I'll tell you the simplified atomic theory, but you probably know that the theory I'm going to give you divides even smaller. And what those particles are, divide even smaller to the point where you're like, I don't even know what a particle is anymore. And that's the joy and craziness of chemistry. So an atom is not a sphere, but let's say, what is an atom? Well, we're going to go one step further and say that we know an atom has some particles in the center of it, and then it has something moving around it. And really an atom is mostly just space. In fact, maybe it's all space, but still an atom is the smallest particle that you can have a substance made up of. And what's the very simplest atom you can have? Well, we call it hydrogen. Hydrogen, the basic building block of the universe. So in a hydrogen atom, we have a particle in the middle that we're going to call a proton. And we call it a proton because we say it has a positive charge. And then there's a tiny particle going around it, and I'm going to represent that tiny particle by the head of a pin. Do you see how tiny that is? Guess what? If the proton of an atom were a lacrosse ball, which this is, the head of a pin would not be small enough. In fact, a particle of dust is more likely to be what the size would be, but probably actually way smaller than that, maybe more like a bacterium, or actually there are people now who theorize that an electron takes up actually no space at all. But we're going to pretend. We're going to say we have this little tiny particle out here. We call this an electron. These two things have a charge. So think of it like an electrical charge where like charges are going to be attracted to each other. And if you have, opposite charges are attracted to each other. Let me get that right. And like charges would be repelled. So if you had two protons, they would want to push apart in theory. And an electron and a proton kind of want to pull together, except for there's movement. So you have this electron this is a simplified representation, by the way, but you have an electron basically zipping around this proton. And that motion keeps it from actually combining together. If they ever did, if you jam them together, guess what you get? You get something, I'll represent it with my other ball here, called a neutron. A neutron is neutral. It has mass, about the same mass as a proton because the electron has such small mass, but it is basically like one proton and one electron jammed together, you get a neutron. So many atoms also have neutrons in their core, and the very most basic atom would say had the same number of protons and neutrons and electrons zipping around it. But that's not always true. We get all different sorts of things. So if you have different sorts of combinations, which thing defines what the atom is? Is it the proton? Is it the electron? Or is it the neutron? It's the proton. We define what an element is based on the number of protons in the atom. So as I told you, the most basic one is hydrogen. It has one proton, one electron, and that's hydrogen. Now the next least complicated, or the next one up, is helium. The next gas we get, it has two protons. Too bad I don't have a better model here. Two protons, two electrons is helium. And usually would have two neutrons as well. But if you get different amounts of neutrons, you just get different isotopes. If one electron gets pushed off, we call those different ions, and you'll talk and learn way more about that. But I just want you to understand this. So as we're starting to understand what these elements are, people took ones that were really common and they said, well, how many protons and how many electrons does, say, oxygen have? We really need oxygen. Well, it turns out oxygen has 8 protons and usually 8 electrons when it's a balanced atom. Sorry, I had to make sure I said the right word, a balanced atom. And so as we start to add more and more and more things to our list of figuring out and weighing and doing experiments and finding out what they are, we started to say, we need a way to categorize these things. We need a way to count them up. And guess what? There were some basic early versions that were very different than this, but we have developed the periodic table of the elements. This thing is awesome. We take every element that we know and we've put it on a table, and the table might seem kind of weird, like strange organization, and you can't see it very well here, but you can look one up. It is organized in a good way to show the relationships of the behaviors of different sorts of atoms. So in this upper left-hand corner right here, you have hydrogen, and you can't see that very well. So I'm going to show you, I've made little tiles. This is a hydrogen, what it looks like on the periodic table. You'll notice the H, this stands for hydrogen, and that's its symbol. We're going to use that in all the times we write down chemicals. Underneath it has its name, hydrogen. Up here in the corner, you see a number. This is what John Dalton created. It's the atomic number. That tells you how many of these there are in the atom, how many protons. So the atomic number of hydrogen is 1. Now, you can get super complicated and get a lot of information, but this is the most basic. Over here, we have a G. That means in its room temperature form that this element is a gas. G is for gas. And down here, you have what we call the standard atomic weight, and we'll learn a lot more about that. You'll notice it's not quite 1 because there are different isotopes of hydrogen in our universe that might get combined together. And anyway, this is the average on the planet, basically. But we have hydrogen, H1. Now let me find another one. What do you think this one might be? So Fe doesn't maybe bring anything to mind, but if you know your Latin, it's for ferrous. And if you know, ferrous materials are things that have iron in them. So Fe is iron. Iron is a metal. How different is it from this hydrogen we just looked at? Well, you'll notice how many protons does it have? I don't know if you can read that very well, but it's 26. It has 26 protons. And over here, you can tell that at room temperature, it is a solid. So iron is a solid at room temperature. It has a lot more protons than hydrogen does. Now, I also told you a little bit about helium at the beginning. So you see helium has 2. Carbon. Carbon's a really interesting one. Carbon's right here on the periodic table. Carbon has 6 protons, and it combines together really well. You'll learn more about carbon and why. But it's trying to fill up its outer shells of electrons, and so it combines in these long chains, and those long chains of carbons become life. We are made up of mostly carbon. I mean, carbon is like a basic element of life in our world, so carbon's a really good one. The heaviest element that we have in any significant amount on our world is uranium. You've probably heard of uranium. Uranium is radioactive. You might think, uranium, that's scary. Well, it can be. You have to treat it right. So uranium, you'll notice how heavy that one is. It has 92 protons. So we make much heavier elements either artificially or you can find them in very small amounts in our environment, but uranium is the one that has the most. So you'll learn that we've organized this whole table with all of these elements in it. But why did we put hydrogen over here and helium over here and not put them right next to each other? Well, it's because of the traits of hydrogen and helium. And so what we do is we organize them according to how they behave. And so we're going to call vertical columns in this table are going to be called either groups or families. And they have different historic names. So it's now called group 1, 2, 3, 4, 5, like this. But they also used to be called like subgroups. So this is also 1A and 2A. And over here we have group 18, but it also might be called group 8A. And so you just have to understand that there's some historic numbers, but the most accepted new way of numbering these groups is just 1 through 18. And so a group or a family, we call it a family because they have similar characteristics in this vertical direction. Anything that's in the same column has similar characteristics. These ones want to combine together. These ones way over here, we call them the noble gases. They're very stable. So anything in this column is a really stable gas. So helium is pretty stable. So it is happy with the number of electrons it has. And you're going to learn a whole lot more about this. But basically, if you have something that wants more electrons or less electrons, then that makes it reactive. It wants to go join together with some other atoms and make something together. So what about hydrogen? Well, hydrogen, remember, it only has that one electron orbiting around it, or not exactly orbiting, but moving around it. It would really like to have two. It wants to be like helium. So what happens with hydrogen is almost always two hydrogens will get together and they'll share their two electrons, and then they're happy because they've got two electrons going around them. But it's still hydrogen, okay? This is all very simplified, I realize, but I just want you to understand. So we have groups vertically and families, and then horizontally, we call those periods, thus the periodic table. And if you're going horizontally across any particular period, and they're also numbered periods 1 through 7, if you're going across by a period, you are going to be increasing 1 in the atomic number as you go across. So 1, 2. This one goes 3, 4. We have this gap, 5, 6, 7, 8. And the reasons for the gaps is we're trying to stick in the elements that have these different shell number of electrons, which you'll learn more about. We have to sort of stick them in and split the table apart to fit them in so that the characteristics are similar. And then like all this stuff at the bottom, it actually fits. We have to squeeze it in there in the table, but we don't want the table to be so wide that we can't print it, so we just sort of stick them below. All right, but this table will be fundamental to everything you do this year. Find a good one, print it out, buy one at the store. There's one in your online textbook. I've included some, and we will also do some coloring of the periodic table so that you get familiar yourself with what the different things on the table tell you and what the different groups are that behave similarly. So this is it. This is chemistry. Remember, we're going to learn about elements. We're going to learn about atoms. We're going to learn how atoms behave and why they combine together. And this whole theory will be the fundamental basis of what happens in chemistry for the rest of the year. Once we understand what these particles are, then we can say, I know why this thing happens. Now, my last note is that protons, neutrons, electrons don't turn out to be the smallest particles. But an atom itself with those particles together, that is the smallest unit that you can divide a substance into or an element into and have it maintain the same characteristics and qualities that it had. So if you get anything smaller than an atom, it is no longer an element anymore. It's no longer the same element. But down to the size of an atom, you can divide any element like oxygen or iron or uranium or nitrogen, and it will maintain its same properties down to the atom size. Beyond that, we're dividing things up into these subatomic particles and things get totally different. Hope that helps. Have fun studying this week.